I want to try to come up with the relationship between torque and angular acceleration. Torque is tau, angular acceleration is alpha. Can we find a relationship between the two of them? That's really what I'm looking for. Can I come up with an equation that will tie the torque to the angular acceleration? Well, let's go back to Newton's second law, which is force, net force equals what? Mass times acceleration. Remember that equation, F equals ma? I think Adam was wearing a t-shirt that says F equals ma a few weeks ago. Was it you, Adam?
Yeah, it's Star Wars.
Yep, F equals ma. I like that t-shirt. So the acceleration is force over mass. We also know A equals what? R times alpha. Remember that equation? Which means alpha equals A over R. This is an equation. Whatever you do to one side, you're going to do the same thing to the other side. So let me multiply or divide both sides by R. If you divide by R, the same as multiplying by 1 over R. So you will have what? A over R F M times R. Now let's compare this to this. What is A over R equal to from here? A over R is what? Isn't that alpha? So alpha equals F over M times R. Remember my goal, I'm trying to find a relationship between the angular acceleration and the torque. I don't have torque. Torque is F times R here. That's what torque is, right? So what about if I take the right side? This is a fraction. What will happen if I multiply the top by R and the bottom by R? I will have alpha equals F times R over mR squared. And what's F times R? Isn't that the torque? And what is mR squared? That's the inertia, the summation of mR squared. So guess what? The equation for torque equals inertia times alpha. That's the equation that ties the torque to the angular acceleration. If you want to find how much torque an object has, know what the inertia is and the acceleration. Again, when you go to change your tires, you see the guys take the drill. It doesn't have a handle. You see the thing spinning and loosening the nuts there. Well, that thing, the socket spinning, has a torque there equal to the acceleration times the inertia. And that's how much torque. And if that value is bigger than what you need to loosen that nut is going to loosen or tighten, based on the value there. Let's look at some examples here with torque. So this is actually really Newton's second law if you want to. Newton's second law, it says the net force equals mass times acceleration, right? We're going to change it to the net torque equals inertia times alpha. This is Newton's second law for rotational motion. for a thing that's spinning. That's Newton's second law. Okay. I'm trying to think. My lawnmower, as an example, that comes to mind. You got a pulley here, and wrapped around it could be your car too. You got the belt in your car, and around that there's a belt that's wrapped around that tight. You know, around the pulley there, spinning there. You see that belt going there. So here we go. We have a belt around a pulley there. And let's say the force being pulled in this direction, or it could be you trying to start your lawnmower when you pull that cord, you know? It's actually a rope tied around the pulley there. If you ever seen it, I don't know if you ever seen that, taken apart. If you have a lawnmower, there's a little string there, wrapped around a pulley there. When you pull on it, you start the lawnmower. So let's say you pull in this direction with the force of, I don't know, 53 Newton. Find, here's the question, find alpha, the angular acceleration, if the pulley here, let's give it a shape. What do you want the pulley to be? You want it to be a disc there? Solid disc? Is a disc with, you have to give it some mass and radius. With mass equals what? 1.3 kilogram. And radius for the lawnmower, it's probably end to end, I'm just wild guess here, probably 10, 12 centimeters. So it's a radius of 6 centimeters.
That'd be 0.06 meters, right?
Correct, 0.06, correct. So first I need to calculate what the inertia for a solid disk, going back to the previous chapter. I should have photocopied that page to have it handy. Solid disk, it's 1/2 mr squared. Should put like a little card there so I know where to look all the time. That's 1/2 the mass, which is 1.3, and r is 0.06 squared. That's 0.00234. That's the inertia. 2.3 times 10 to the minus 3. Kilogram meter squared. I'm looking for alpha. That's the equation I'm going to use. I don't know what the torque is, because if I know what the torque is, I can find alpha. Can we calculate the torque? The torque, remember, this one's going to spin around this point, so I need to know what that distance. This is the r there, the radius. So the torque is that force, which is 53 Newton, times the radius, which is what? 0.06. Torque equals F times R. .18 Newton meter. Can we get what alpha is? Torque equals inertia times alpha. We know what the torque, 3.18. We know what the inertia is, 2.3 times 10 to the negative 3. Can we get what alpha is? Alpha equals wow, we got a large number. You got a big number? 1382.6. Two significant digits, 1400 rad per second squared. Let's take another example there. Uh-oh. Let's see. Another one. Let's say you're holding a sign in your hand. You're holding, I don't know, a golf ball. You're going to drop it. I was watching golf last night, or yesterday afternoon, and Casey got the ball on the tar, so you're going to have it drop. You hold the ball in your hand, your arm straight out, and you drop the ball. So your hand looks like this, straight. That's your hand. And to get the ball in your hand. It looks like you got huge arms, but there we go. You get that golf ball and you're going to drop it. Your arm is horizontal. Let's say the distance from the ball here to your shoulder, the pivot point, that's your joint here, shoulder here, that distance between is 0.74 meters, 74 centimeters. And your arm is not really uniform. Let's say the center of mass for your arm is right here. The weight of your arm, if we were to cut your arm and put on a scale, they wouldn't do that, but if we were to cut it there and put on a scale, it has a mass, the weight equals mass times gravity. Let's get some numbers here. Let's take the tennis ball out, actually. You're just going to hold your arm there. Just going to hold your arm. Now, how come your arm is not going down? Because if you let it go, what will happen? It's going to drop. What makes it drop? Why does it go down?
Gravity.
The weight of your arm, gravity pulling on it. Okay. Your arm is at rest initially. You said let it drop freely. It moves down. It begins to rotate around the shoulder joint. That's the joint right here in your shoulder. And that arm will go down. Boom. First question, find the initial angular acceleration of the arm. Part 2, find the initial, instead of angular, we'll use linear acceleration of the arm. And it says in this problem, assume the center of mass in the middle of your hand. Assume the center of mass here right in the middle. The mass of the arm is concentrated at its midpoint. We know the arm is not uniform, but for the sake of, otherwise we have to know where. But for this is assume it's in the midpoint. You know we're going to need the inertia. And the other thing we have to assume beside that the arm for the inertia is uniform, rod. Assume the arm is a uniform rod. We know it's not uniform. So two assumption. Assume, I'm missing E here. Assume the mass of the arm is concentrated at its midpoint. Assume the arm is a uniform rod. Two things to assume. So this is what we're doing basically. We're treating the arm as a rod, like this, uniform, has the same mass, the center of it right here. So the weight of that is mass times gravity. Do we know what the mass is? No. Mass is unknown. So we'll leave it. We're also making this the pivot point right here. The joint. That's the joint right there. So it's going to spin around that point. So this will have actually a torque that will be what? Clockwise or counterclockwise? Clockwise. So the torque here, there's L here, R, whatever you want to call it, and this is the weight. Force times R. The force is the weight, which is mass times gravity. And what is the radius from here to there? Isn't that half the beam? Half of this? I'm going to use L over 2 for now. I'll plug in the numbers later. L is the distance from here to there, the length of the arm. I know it's 0.74, but let's leave it as L over 2 for now. That's the torque. So it's 1/2 M times G times L. So we know what the torque is. I didn't give you the mass intentionally because I don't think we need it. In Newton's second law, if I'm looking for the angular acceleration, in Newton's second law, it says, you know what? The torque is equal to what? Inertia times alpha. So if you're looking for the angular acceleration, you need the torque, you need the inertia. If you know these two things, you can find alpha. Well, I know what my torque is. 1/2 M times G times L. Do I know what the inertia is? Well, you're treating this as an arm. This is my arm. It's spinning around this end. So the inertia for a beam that spins around its end, I think it's 112 ml squared, I think. Let me double check. around its end, no, it's 1/3. Am I blind? Is it 1/3? 2/3? Can't really see it. 1/3 ml squared. 112 around the center. 1/3 ml squared. So the inertia from the book, it's 1/3 ml squared. The mass of the arm times L squared. So that's your inertia. Plug it in. And what do you notice about the masses? They cancel each other out, right? What else cancels mathematically? This L cancels one of these L's. Get two of them here. So you have 1/2 times G equals 1/3 times L times alpha. Now plug in the values for them and you know what alpha is. I could have plugged in the numbers early, but I'm trying to show you we don't need the mass. G is 9.8. .9 equals 0.74 divided by 3, 0.25, approximately 0.25 alpha. What is alpha equal to? 19.9. Two significant digits, alpha equals 20 rad per second squared. That's the angular acceleration. Next part, what's the linear acceleration? The linear is what? A equals R times alpha. R is actually the length of your arm. That's what R is. Like if there was a ball in your hand and you're going like this and you let it go, it's going to have an acceleration. It's leaving the tip of your hand. So it's not, the ball is not going to be in the center where the mass is. It's going to be in your hand, in your fingers. That's why R for that is going to be L times alpha, which is 20, and that's what the linear acceleration. .7, and again, if you want two significant digits, that's 15 meter per second squared.
And what if we weren't dropping the ball?
Oh, you're looking for a tangential acceleration of the tip of your fingers. You know, if you're looking for a spot somewhere else, that's different. If I'm looking right there for your elbow, like something attached to that, then that'll be that distance. R will be half of L. You know. I'm going to do one more topic, and then I'll call it a done deal with this one, I think. And just for those people only going to be with us for Physics 1, I want them to have some understanding of this.